Welcome to the AIM booth here at SMTAi 2017. I'm joined by Dr. Mehran Mallekian. I need to read this, I'm afraid, just to make sure I get it correct.
Mehran Mallekian.
Okay,
yeah.
Excellent. So welcome to Global SMT. We're here to talk today, Mehran, about a new lead-free solder alloy that you believe outperforms SAC 305. It's the REL 22.
Right.
Can you tell me what are the key features of this alloy?
Right. This alloy is designed for high reliability applications where you have a harsh environment, and SAC really does not perform well in this harsh environment. This alloy actually overcomes those shortcomings of SAC 305, or SAC, basically high silver SACs.
So what is it? Does it specifically make it stronger, more conductivity? What are the...
Right. In order to address the strengths of REL 22, I would like first to mention the drawbacks of SAC and how we overcome the drawbacks. SAC 305 is actually the standard lead-free alloy. It performs extremely well in many applications, but for harsh application where you have high temperature and SAC easily creeps, and by aging the microstructure of SAC is degraded and the mechanical performance is also degraded. So based on that, we developed, in our development for new alloy, we actually overcome the low strength of SAC by aging, which by adding some alloying elements, we actually overcome that. For instance, bismuth is a strengthener to lead-free alloy. By adding bismuth, you can basically have a solid solution strengthening in your alloy, but if you add too much bismuth at the same time, you get also brittleness, which is not good. So we had to optimize the amount of bismuth in new alloy. So we did a systematic study on that, and we came up with the optimum value or optimum bismuth content. So that's the strength. But when we talk about reliability, we also talk about long-term application in harsh condition. So you need to have a good creep performance and also good thermal fatigue. And bismuth helps, but is not the 100% what you want. You want some other alloying elements and grain refiners. REL 22 actually has some other alloying element and grain refinement.
Okay. Well, I realize for proprietary reasons you don't want to go into detail on what these other elements are. But going back to what you said about the degrading of SAC 305, it's purely over aging, or is that over thermal excursions? If it does a lot of high thermal excursions, it degrades faster, or is it just purely aging?
That's true. I mean, aging, if at room temperature, also it degrades, but it takes longer time. But if you do at a higher temperature aging, then you see the result much faster, or degradation of the SAC much faster. So overall, to answer your question, yes, aging in any condition, because lead-free or solder alloys are low melting temperature, and they are under aging and recrystallization all the time, even at room temperature. So yeah, SAC 305 degrades by time, at higher temperature faster, and but we have done the study comparing the aging effect on SAC versus this REL 22. REL 22 actually did not show any influence, any degradation under aging compared to SAC, and we compared the creep performance of SAC versus REL 22. In as soldered conditions, SAC performs very well, as good as, almost, not as good as, but close to REL 22. But while once you did aging, a few hours aging at a bit high temperature, SAC degrades promptly, but REL 22 performs similar to unaged samples.
So what sort of testing did you do? What thermal excursions did you do? What limitations?
So in order to develop an alloy, we do many testing. I mean, many mechanical testing and microstructural evaluation and thermal cycling. So just to summarize, we do tensile tests to measure the strength versus SAC and also toughness. we do high temperature thermal cycling and thermal shock test to see how reliable it in real condition, actually, real situation. We go from we have done a test, let's say, a standard test, actually, minus 40 degrees C to 125 thermal cycling, and Rel 22 outperforms SAC by a big margin, like 2.5 times better than SAC 305. Right. Actually, it's a recent result we have got on that.
So which markets is this specifically aimed at? And you're looking at automotive, I would assume?
Yeah, automotive industry and high power LED applications. Okay. So any application or avionic, any application that they need a high reliable alloy that can withstand for a harsh condition for long term. So
I mean, LED is obviously a big problem. I mean, they advertise that these lamps last 25 to 50,000 hours, you know, sometimes, but the solid state electronics only last 5,000 hours. So using your Rel 22, are you able to measure a longer lifespan on the solid state electronics?
Well, these are all, I mean, accelerated testing that we do, right? Everyone. Because in order to give you 100% answer, you have to wait 20 years and after they could compare. But those accelerated thermal cycling tests, actually tomorrow I have a paper on that to show, particularly on LED, that Rel 22 outperforms SAC in a thermal cycling on LED component, minus 40 to 125 degree after many thousand cycles. So these are accelerated tests, and we can extrapolate, you know, those accelerated tests to real life. Yeah.
Okay. Well, it looks like a really interesting product. I want you to thank you for sharing the information with us, and look forward to your paper tomorrow.
Thank you. My pleasure.